Hello, my name is Josiah Brell, and I'll be going over problem 8-7, part A, from Fogler's Elements of Chemical Engineering. Alright, so basically we have the reaction here, A plus B goes to C, and it is being carried out in a flow reactor. It's a elementary reversible liquid phase reaction. It's got the double arrow here for reversible. It's carried out adiabatically as well. So basically, we have an equimolar feed of A and B coming in at 27 degrees C, which would be about 300 Kelvin. The entry in volumetric flow rate is given as 2 dm cubed per second. We're also given our entering concentrations of A and B, and they're equal. Both are 0.1 kilomole per cubic meter. We're also given information about the heat of formation and specific heat, as well as the energy and the reaction coefficient. So basically what this problem is asking us to do is plot the conversion and temperature of the PFR up to a reactor volume of 10 cubic decimeters when the Kc is equal to 10 meters cubed per kilomole at 450 K. So we're basically plotting both the conversion and the temperature with respect to reactor volume. Then we're also asked to plot the equilibrium conversion profile, which is the equilibrium conversion with respect to reactor volume. So basically what we're going to start out doing is finding the change in specific heats, and that's given by this formula right here, which would be your product minus your reactants. So CPC minus CPB minus CPA, that turns out to be 0. Moving on, we then want to find the delta H of reaction. So again, that would be product minus reactants. This is all information given to us above, so we can solve that out to be -6 kilocalories per mole, which is the same as -6,000 calories per mole. Just to make it easier further on in the problem, we'll just convert that to calories per mole. The rate law for this equation is, for elementary equation, is given as -RA is equal to K CACB minus CC over KC. Equilibrium conversion, X equilibrium is equal to KC over 1 plus KC. We can also set up our balances for the different components for the concentrations with respect to conversion. So we have Ca is equal to the initial concentration of Ca times 1 minus conversion. Cb would be the same because they're fed in equimolar rate. Cc would be equal to CaO times the conversion of X. So we can then do our adiabatic energy balance, which is equal to this equation here. Temperature is equal to initial temperature plus conversion times the change in the heat of reaction at the initial temperature. This is divided by the sum of the specific heats plus conversion times the delta specific heats. We know all this information here. Here it all is defined down here. And then we can plug it in. You'll notice here both of these values are 0, so the delta Cp and the theta for component C. So we can just cross those off, make it a little simpler. We end up getting this equation for temperature. So temperature is equal to 300 plus 200x. So we can then go on to use our volumetric flow rate equation. V naught is equal to FAO over CAO, which is the feed over concentration. We can manipulate that because we know VO and CAO. We can use it to find FAO. So and that's done right here. So this is our VO right here, 2 decimeters cubed per second. This is our CAO, which was given earlier in the problem as well, 0.1 kilomoles per cubic meter. And then we'll just do a couple unit conversions to convert our decimeters cubed and convert the kilomoles to moles to make it cancel out, end up getting a feed of 0.2 moles per second. Now we can combine everything so we can get a nice form for our rate law. So we can combine our rate law as well as our mole balances here. Plug them all in, plug the mole balances into the rate law, and we can get our final rate law to be negative RA is equal to K times CAO squared, 1 minus conversion squared, minus CAOX over KC. So next what we need to do is find a better expression for our rate constant as well as our equilibrium constant. We can do that through the use of the Arrhenius equation. Alright, so here's the Arrhenius equation here, kind of set up. So the R for this equation that we're going to be using is 1.987 calories per mole Kelvin. So we can just find a R value that works with our units, as most of our units are using calories. We want an R with units of calories. So then we can raise both sides to the E here to get a little bit better form, and then just multiply both sides by the K at your first temperature to get an expression for K at your desired temperature. Then we can plug both these in. So over here we have the reaction constant K. So that's plugging in the given E from the beginning, the R, as well as the given rate constant at the entering temperature. And here we're plugging in the information for the equilibrium constant. So we're given at the beginning that the equilibrium constant is 10 at 450 K. And we also solve for the delta H of reaction earlier as well, then again the R. Then we also need a mole balance for the PFR that we can just use as given. dx dV is equal to negative RA over FAO. So that's pretty much all the handwork. We can now go into Polymath. This is how I plugged it in. A couple different ways you could plug it in. You could also kind of define different things as variables and then define the variables lower down, but pretty much plug just about everything into the equation. So up here we have our mole balance. Here we have our volume, so we're wanting to go out to a volume of 10 decimeters cubed. So we've got V final is equal to 10. Our initial conversion we also have to define, and that's 0 because there's no conversion at the beginning. Right here we have our rate law defined, as well as our initial concentration, which was given, and our FAO, which we found. These are two rate constants expressions. The temperature expression, which is from the energy balance, as well as our equilibrium conversion expression. So after solving that, this is the report that Polymath gives. So just kind of everything solved out. We can see what everything gets to, as well as our differential equation, explicit equations, everything that we set up. We can also get graphs from Polymath, so this is what the question asks for. So here we have a conversion with respect to reactor volume. So as we can see, as the reactor volume increases, our conversion also increases. So at the beginning we're at 0, and then it increases to about 4.5 times 10 to the negative 3. You can also plot temperature versus reactor volume right here. So again, it's increasing as the volume of the reactor increases up to about 301 K. Then we can also plot our equilibrium conversion versus reactor volume. So as our, once again, as the volume of the reactor increases, the conversion also increases. All right, thank you.